Let's go ahead and talk about nuclear fusion and fission. What exactly is nuclear fusion? Consider two light nuclei, right? Something along the lines of hydrogen 1 or deuterium. If you were to combine these two light nuclei somehow through a process, the combination of these will result in a larger nucleus. Not only that, it would also create a specific amount of energy, and this process would be then known as nuclear fusion. So nuclear fusion is when you join two light nuclei together, or you fuse two nuclei together to create a bigger one. This process creates a specific amount of energy as well as a new nucleus, which happens to be, in most scenarios, helium. Let's talk about one of the main examples through which this process happens, and obviously that is the sun. The sun is one of the most successful factories of energy production in the solar system, facilitating this process through almost fusing 500 million tons of hydrogen almost every second. The process is kind of as follows. Imagine deuterium, which is hydrogen 2, basically hydrogen with a mass number of 2, mixes up or fuses with hydrogen 1. What is produced is a helium nucleus as well as some energy. This energy, of course, in the form of sun is, in the case of sun, is light as well as heat. Now, one thing you need to understand about fusion is in order for two nuclei to really fuse together, they need a lot of energy. Because technically, there is an electrostatic repulsion between the nuclei of these particles, since they're both, you can imagine them to be like positively charged, and then there's obviously a repulsive force between them, right? Because unlike like charges actually repel. So you need lots of energy to actually cause the fusion to happen. This amount of energy is usually achieved through a specific amount of kinetic energy, which is about 1 mega electron volt. Once these particles get to about 5 femtometers, then the process of fusion can take place. However, we know that on planet Earth, this process is not going to happen anytime soon because obviously we don't have a place where we can produce the exact amount of thermal energy required to carry out this process, whereas the sun obviously has that thermal energy. So what are the positive points of nuclear fusion? First of all, the product that is created is helium, which is an inert gas, so it obviously just goes up the atmosphere. Secondly, there is a decent amount of energy produced, and you can use that energy for lots of good purposes. The negative points about this process is in order to carry out this reaction, you need a high density of protons to actually sustain the fusion reaction, as well as the high temperature required to carry out the reaction, which is kind of way above millions of kelvins, and that's kind of not realistic at the moment with the conditions we have. So that's why nuclear fusion, for now, happens to be a process that happens in the sun, and we cannot really commercialize it and start producing electricity from it. And so that's the negative of the nuclear fusion. Temperature and high density of protons are required to sustain the reaction. Let's go ahead and take a look at some examples of nuclear fusion's reactions. So, let's say deuterium mixes up with another deuterium, and basically a helium atom is produced. What is the missing element? Well, if you add up the mass numbers on the left side, you get 4. If you add up the atomic numbers, you get 2. So the same thing should be happening on the right side. We currently have one missing element for the numbers to match so that their atomic numbers become equal, the mass numbers become equal, but their atomic numbers is already equal. And the only element that we know whose mass number we can consider to be 0 is a neutron. And that will complete the reaction process. Let's do another one. Let's say an element is actually fused with a lighter element is fused with tritium, and that produces helium, and 1 neutron. So what is that missing element? Well, on the right side, we have 5 for the mass numbers. If we add them up, we have 2 for the atomic number. While on the left side, we have 3 as the mass number. So we're missing an element that has 2 as its mass number, obviously, and that happens to be deuterium. And if we consider the atomic number of deuterium, which is 1, to be added with tritium, which is 1 as well, you will see that the atomic numbers start matching as well as the mass numbers on top. That's it.